All right. So now I will begin our session on quantum gates. After this, for about 30 minutes, I will have a doubt clarification session. So in case you have any questions, you want me to do something extra, we can go ahead and do that. So welcome to day 2 of the IBM Qiskit Fall Fest at our APU College. I'm glad to have you all back again. So now we're going to be we looked at quantum states, what quantum bits can be like, how you can manipulate, we didn't learn how you can manipulate them, but how they present as, how you can measure them. Today, we will learn how to change it from one state to another. We can see, before I continue, I'm just going to address, a lot of people are asking me where we can get the recorded video of the sessions. I have sent an email with link, and if you have not received that, I will send it over again, but please check your inboxes for an email from me. I'll just send over the link. I'll send the link at the end of the session, if that's okay. So coming back to this, yesterday we learned about quantum bits, how they present us, and how we can measure them in different bases. Today, we're going to be learning about the circuit. So we're going to learn how we can change a state from one given state to another. If we want a 0 to go into superposition state, a 0 to go to the 1 state, or if we want to interact between two bits. If we have two qubits and we want to have some sort of interaction between them, we can also apply a gate. And that's what we're going to see here today. So before going forward with how gates actually work, let's look at the circuit model. So this over here is what you'll see as a circuit model. So we send in our state psi. So usually before computation, this is going to be 0 because 0 is the ground state. So before we apply any gates on it, it's generally the 0 state. Then this box means that we apply our gate on 0. So G1, gate 1 is applied on 0. And that's how we denote it. So G1, instead of 0, I'll just say psi, G1 of psi. So now over here, this is our state. So after gate 1 has been applied on it, it's now G1 of psi, which means G1 has been applied on it. So it's a new state. Then 2. So once again, G2 is applied on G1 psi. So G2 is further applied on our state. Remember how when we apply a gate is a 2x2 matrix. So A, B, C, D. And if we have our quantum state E and F, we're going to get another vector, say G and H. So when we apply a gate on a state, even mathematically, we are going to be getting another state, another two-dimensional vector. And so when we apply n different gates, we are going to get Gn, Gn minus 1, ... all the way to G2, G1, and psi. So I hope the ordering is clear because it goes the opposite way. So the gate that is applied first is the closest to psi. So G1 is applied first, then G2, then G3, Gn minus 1, and Gn. So this is our new state, psi prime. So this is our circuit model. This is essentially a pictorial representation of how qubits can be manipulated. But the thing is, this model is also followed even for classical computers. Followed even when we consider our normal computers, where the only thing that happens is the change between 0 and 1. So different bits can interact, And you can also have a single bit gate. For example, one of our most famous classical gates is the NOT gate, which literally does just that. It creates it to what it's not. So it goes from 0 to 1. If it converts 1 to 0. So if I send over here, 1 is going to come outside. 1 is the result of applying our gate. If we apply 1, what's it going to be? 0, precisely. So that is a very simple gate. So now let's go on to quantum gates. So before we do, I hope all of you remember our Ket-Bra notation. So I believe we'll go over that later. So just a reminder, we're going to be using Ket-Bras coming very soon. So one thing about the circuit model when it comes to quantum computing, that it needs to preserve the inner product of the Hilbert space. So that is one of our postulates of quantum mechanics. And what does that mean? So we learned what the inner product was yesterday. But what this says is that if unitary evolution, which means if we change two states that we take the inner product of, it should retain its previous inner product. So let's see that. So we now have, So we now have states alpha and beta. So now we see that the inner product of alpha and beta is P. Alpha beta is equal to P. Now let's perform unitary operations, or we'll apply our gate. A unitary evolution is just a fancy way of saying quantum viable gate. So a unitary evolution is something that truly can be made in a quantum manner. So our unitary evolution. So now let's apply it. Let's call it G, as we've been seeing so far. So let's apply G on alpha and call our new state alpha new. And let's apply G on beta and call it beta new. So now what we observe, that if we have a valid unitary evolution, if G is a evolution, then alpha new, beta new is also going to be equal to the dot product of the inner product of alpha, which is P. So we'll observe this coming forward, but this is something to keep in mind. Whenever we have a quantum gate, it must preserve its inner product. This is not observed in traditional computation, but in quantum computing, we need it because this is a quantum system. So we cannot lose information when we do a computation on it. So let me just clear the ink off the screen. Oops. So that is our third postulate of quantum mechanics. Valid quantum state transformations are given by unitary operations. So unitary operations preserve the inner product, and that's what the formal definition is. So since quantum theory is unitary, they ensure that our quantum state remains valid. One more thing that unitary evolutions do, or these quantum gates do, is that it maintains normalization. So remember that we had to have all of our quantum vectors be of length 1. However, if we had a matrix something like this, 2, 0, 0, 2, 1, 0. So what would this be? 2, 0. So is this a valid quantum gate? Do you think it might be a valid quantum gate? It's all right if you're wrong, but okay, I'm seeing some yeses and some nos. So why is this a quantum gate or not? Let's see. So yesterday we learned that all of our quantum bits or vectors that represent our quantum bits need to be of length 1. So what happens here? So we have this, which is 0 state, and this is our gate. But what we get is 2, 0. 2, 0 has the length of 2. So our gate has elongated our quantum vector, which is physically, and hence this is not a valid quantum gate. So that is what we mean by it maintains normalization. So when we have a quantum bit, when we apply G, our gate G to a state psi, and we get psi prime, if we get a new vector, new state, this also has length 1. And so G must be a normalizing gate. And so if you remember from last class, we had equal to 1. For all states psi, this would hold. So now from what we just studied, if we apply unitary gates on this, so now if you observe u of psi nu, when you apply u on it, so now so this is just pretty much the Dirac notation way of we've applied u to both the ket and the bra. So I'll go over this once more, but just try to follow along. So what is this essentially? We've applied u to our first q for our bra, and we've applied u to our ket. So this should give me the same thing as psi nu, which is the. So I'm going to explain this once again, because I think I went pretty fast with the explanation, and I will go over normalization again. So when we apply, so maintains normalization means that when we send in our state psi and we apply a gate to it, then we get a new state outside, right? Our new state psi prime. Psi prime also length 1. From yesterday's class, we learned that quantum states are unit vectors in the Hilbert space. Unit vectors, so they are of length 1. So our gate cannot change the length of our psi. So psi cannot, when psi becomes psi prime, applying G on it should not change its length. So length 1, psi is length 1, psi prime must also be length 1. And that is what we mean by normalization. So now coming to this notation, I'll just go over it once again. So what we just saw was that when we applied u to alpha, it became alpha nu. Or rather, let's take the same notation that's on the board. So here we have psi and we have phi and psi and phi. So say we have u unitary applied to psi, and we get psi prime. Okay, there is one question. When psi is transformed, why is it called psi prime and not psi nu? I am using them interchangeably. So if you find nu better, I can use that. It's more of just a discrepancy between slides. There's no particular reason why I'm using prime and new. I can call it anything. So I just want to indicate that this is a new one. This is new state. And this is our old state. What is applying a gate and a unitary? Good question. A gate and a unitary is pretty much the same thing. So our gates must be unitaries in quantum computing. In classical computing, gates do not necessarily have to be unitary. Unitary means it does these two things. So because it maintains normalization and maintains the inner product, any gate that does so is called unitary. Classical bits, our gates don't have to be unitary, but in quantum, it has to be unitary. All right. So before I address the rest of the questions, I will go through the notation because that should answer your questions. All right. So we have u of psi or psi nu, psi prime, you can call it anything. So now what we want to indicate is that u of psi, what u of psi means is that it is the length of, it's the magnitude state. So what we're just indicating by this is equal to 1. Psi is equal to 1. And that's what we denote over here. So we're essentially, these are all just different ways of saying the length is 1. All right. So now coming to this notation. So I'm pretty sure a few of you are confused. Why do we have 2 bars? So these 2 bars are primarily indicative to show the magnitude of gates. And when you have the best way to explain it is because of complex numbers, we generally indicate it with 2 bars. I can get into it a little later into the session at the end, if that's all right. But essentially, this is just formal notation. When it complex numbers, especially when it comes to multiplication of these gates. So now I will address what this U dagger is. So if you remember yesterday, we covered what bras and kets were. We had alpha, we had as the ket, and what was our bra? Alpha was equal to A1 ket, A2 ket, A2 dagger rather. Sorry about saying ket. So this is our bra. So essentially what the dagger represents is that it is the ket version, but of a matrix. So we take our complex conjugate transpose of our unitary. So I think this will be made clear as we go forward, but essentially, so this is This is how we defined our bras and kets yesterday. So now let's look at, for example, U is the gate. Zero, zero, or let's just have it as I. So now let's look at U dagger. So now we're going to take the complex conjugate of each of the values and take the transpose. So if you take the transpose, it's going to be the exact same. But if we take the conjugate, it's going to be minus I, 0, 0, minus I. So when you multiply U and U dagger together, we get the identity matrix. So that is also matrix, absolutely. So now once again, coming to normalization. So for example, we have, oops. Yeah, all right. So now we apply U to psi. If we, is psi prime, psi nu, whatever you're more comfortable with, you can have that. And now if we want to take the bra version of this, so remember it is going to be or rather, sorry, this is going to be just psi. So if you have a book and a pen, you might want to write this down. So if this notation confuses you, don't worry too much, because we won't be writing. Is my voice, oh, sorry. Is my voice still breaking? Sorry, my internet's pretty bad today. Is it a little better now? Okay, just let me know in case you can't hear me on something, and I'll go over it again. So in case this notation confuses you, don't worry too much, because we will not be particularly going into the dagger format anytime in this, for your information. So similarly, maintaining inner product, as we just saw, U of alpha is, say, alpha nu. You can call it alpha prime if you want. U of beta is equal to beta nu. Beta nu as a ket is also going to be the same as beta and U dagger. So if we have the inner product of alpha nu and beta nu, it's equal to alpha nu and U beta nu. So according to the property of dagger times U is the identity matrix from this, we get alpha nu identity matrix beta nu, which is equal to beta. So yeah, don't worry about this if you're a little confused. This is just a very formal notation on how this works. So here it's actually alpha and beta. So I can go over this once again later if you are confused again. So this is the identity matrix in case this was not noticed. And these two lines are to denote magnitude. It's similar to how we did alpha yesterday, but since we're doing matrix multiplication of matrix multiplication, we generally tend to put two of them. So yes, it's the modulus. So once again, I'll go over this yellow box, but it's okay if you don't understand just yet. Any unitary can be constructed this form. So if you remember our ket-bra notation yesterday, this looks awfully similar to our ket-bras. So does anyone remember what a ket-bra produces? What sort of structure? Is it a number? Is it a vector? Is it a matrix? All right, I'm seeing the right answer. It produces a matrix. Gates are matrices. And so is essentially how we can construct our unitary. So it must be of the form psi 0 ket psi and 1 ket psi perpendicular. So psi orthogonal. So we can take any state, we can take 0 and we can take any random state psi. Then we can take another state which is orthogonal or perpendicular to our state psi and put it over here. And this is one valid unitary transformation. So we'll see that coming up very soon. A quick refresher on ket-bras. It's, as we just saw, as everyone has clearly pointed out, it is matrix multiplication. So A1 times B1 conjugate is over here. A1 times B2 over here. A2 times B1 conjugate over here. A2 times B2 conjugate over here. So pretty simplistic. We can try that out with our 0, 1, 0 ket-bra. So we have 1, 0, 0, 1. So on multiplication, we get 1 times 0 is 0, 1 times 1 is 1, 0 times 0 is 0, 0 times 1 0. And that's what we see over there. So the interesting thing about this sort of Dirac ket-bras is that, oops, cancel, just 1 second. All right, so one important thing to note is that when we have a ket-bra, the implication is when we apply this, say, or rather the general matrix, when we apply it on state beta, it turns into alpha. So this is the implication. So when we apply this gate on, say, beta, it will turn into alpha. So can anyone tell me what this gate will do? This is not a gate yet, as we'll see further. But if we matrix on this, on which state, if we apply it, will it turn into something else? So if we apply it on alpha, what is beta? What is alpha and what is beta? What does it turn? What does it turn one number to another? So I see one right answer sent to me personally. So this is not a gate yet. That's one thing to note. So I want to know what it turns into. So, okay, I'll make this a little simpler. One person sent me the right answer, but otherwise I'm seeing a little bit of confusion. So if I apply this on one, this particular gate, if it's applied on one, what happens? Yes, so it becomes 0. So when we have a gate, when we have alpha, beta, what it does is when it's applied on, say, beta, it becomes alpha. So when we have a gate that is like this, beta becomes alpha. So this, when we apply this on beta, it becomes alpha. What happens in our 0, 1 Ket-Bra case? 1, whenever this gate is applied 1, it becomes 0. So when we apply 0, 1, 0, 0 on 1, when we apply it on 1, what happens? We can see it through matrix multiplication. It becomes 1, 0. So now the only thing it does here is it converts 1 to 0. We don't know what it does to 0. We don't know if it turns 0 to 1 yet. All we know is it turns 1 to 0. So that's all this implies. Here as well, in this case, it turns beta to alpha. We don't know what it does with any other state as of now. It just, whenever we apply this gate on beta, it turns into alpha. So is that clear? Are there any questions? Do you want me to go over this again? Just feeling. Okay, a brief explanation once again. So we know our Ket-Bra gives us a gate, or not yet a gate, but rather just, we can consider it a regular gate. So a Ket-Bra gives us a matrix. So alpha, beta, the Ket-Bra of alpha, beta gives us this over here. So it gives us an operator that acts on states. So if this acts, the only reason we write it out in Ket-Bra notation is that it indicates that when we apply this operator on beta, on the state beta, it turns into alpha. So let's consider this to be the gate G, right? So when G is applied to beta, it becomes alpha. Same thing over here. 1, 0. So let's consider this G, again, G2. So when we apply G2, the only thing we know about this matrix right now is that G2 applied on 1 is going to give us 0. So that's all the implication is. So when you look at the Ket-Bra, just look at the second entry. Second entry is going to become the first one. The bra is going to become a ket if we apply our operation on it. So it is not yet vice versa. So 0 does not become 1 in this case. So this is just reduction. So we will see how it works, how 0 can become 1, how to implement a NOT gate very soon. So now this is exactly what we just saw. This is going to be equal to 0. And this is what we just covered. So once again, what does this become? Just to check. If we apply the same gate twice, will we get the same value back? Not yet, not with these gates. But if you have a valid unitary transformation, you will. Okay, so this is alpha. Everyone's on the same page. Correct. So, all right. Now, we come back to what we covered in that yellow box initially. Any unit can be constructed in this form. So 0 becomes a state psi, and 1 becomes a state that is perpendicular to it. So what did we just see? We had only seen in this previous format, we had seen 0 and 1, right? So let psi be 1. What is the state that is orthogonal to psi? We saw it yesterday. What, when you have the dot product for one something else, it's 0. Perfect. 0. So we know that these are orthogonal. When you take the dot product between them, it is 0. So one way we can construct a valid unitary transformation is by taking 0. This is 1. So 1 plus 1, 0. So this is a valid transformation. What we saw previously is not a valid transformation. It was just an example. So what does this do? It transforms 1 to 0 and 0 to 1. Isn't that what we just saw as the classical NOT gate? The NOT gate converts 0 to 1 and 1 to 0. What happens if I apply this gate that we just created 2 times? What happens if I apply it twice? 0 becomes 1, 1 becomes 0. If it's 1, 1 becomes 0, 0 becomes 1. So you get back the original value. Exactly. So let's see what this gate is called. So this gate is called the poly X gate or the bit flip. So this is the quantum analogy of the NOT gate. So if we have 0, it gives us 1. If we have 1, it gives us 0. And let's write that out. So if just a little bit of matrix multiplication for basic numbers, you can go ahead and do that with me. This is 1, 0, 0, 1 plus 0, 1, 1, 0, which is equal to 0, 1, 0, 0, 0, 0, 1, 0. And then finally, you get our desired matrix form of the gate, 0, 1, 1, 0. So this is our poly X gate. We can also denote it by X. So X of 0 is 1. X of 1 is 0. So this is how we write it out. So once again, it's very similar to what we just saw. 0 the 0 ket becomes the 1 ket, one state, 1 becomes the 0. So the representation is going to be, if you're writing it out on a platform like Qiskit, you'll generally see this X. So it's just a gate with X written on it. And then if you see in more scientific papers, it's going to be this. In this case, is it vice versa? Yes. So 0 becomes 1, 1 becomes 0. So because both are explicitly mentioned, if I had something like 1, 0, this wouldn't be a valid gate. But we have both. So we have 1, 0 and 0, 1. So since 1 and 0 perpendicular to each other, orthogonal to each other, this is a valid transformation. So I'll just see if I have any quizzes that I have. All right, so I'll launch one quiz that will probably test your previous knowledge rather than the poly X gate, which I forgot to launch before. But this is based on a property of unitary gates. So let's see if you've understood that portion of things. So if we have transformed 2 qubits, then what is the dot going to be? The first one's psi. Hold on. Let me see if I can end that. Give me 1 second. Let me see if this works. Oh, great. This is a Zoom issue. Let me see if that works. The first one is not minus, but rather psi. I'm not sure why it's appearing as minus when I launch it, but it's u of psi, not u of minus. So notice the order of A and B. I think a few of you might be a little confused about the ordering, but otherwise. And someone has asked, shouldn't it flip around the z-axis? In case you did notice the block sphere yesterday, that's a good question, but it actually flips. The z-axis contains 0 and assuming you did go through the slides, I'm going to just quickly mention this. It's not important if you haven't. So our 0 and 1 lies on the z-axis. So this is z. X-axis is here, and so is the y. So if we have a state, if it flips around the z-axis, it's just going to be kind of rotating about its own axis. If it flips around, say, x, it's going to flip like that. So 0 becomes 1, 1 becomes 0. Okay, so I'm going to end the poll because in a bit, rather, I see some confusion. So I'll just go over that quickly once before going ahead. But just remember that the inner product is retained when we apply a gate on 2 different states. Okay, I'm going to end the poll now. So there's quite a bit of conflicting remarks going about. So let me just cover that quickly before we go ahead. Let me see if I can So I've written A, but you can take it as anything. A is equal to U of psi. Sorry, it's for whatever reason, my psi's are turning into negative signs in some places only. Beta is equal to U of phi. So now what happens is AB. So we saw that the inner product is maintained. That's what we see over. So this is equal to psi U dagger U of phi. This is the identity matrix. So it's going to be this answer. So a slight majority of you have picked that answer. But this is just, again, fancy notation for just saying that the inner product is maintained. All right. Do I have another question? Okay. All right. Coming back to our Qiskit, do we have any questions before I move ahead regarding the poly Qiskit? So this is just called the bit flip. Do you want me to go over it once again? Just feel message me privately or on the group, and I can, on everyone, and I can see it. All right, are we good to go ahead then? Is it important to put the lines between? It's optional. Those lines are. Do you mean these one? Do you mean this one? That's the identity matrix. Yes, that's just the identity matrix. So the identity matrix essentially is a matrix that does nothing. So you can pretty much ignore it. Yes. Oh, so one thing I want to make clear in case you are a little confused about the identity matrix is that the identity matrix is something that does nothing. So if you apply I to say some state, it's going to remain the same thing. So I think I should have made that more clear because first years might be a little confused on that. So the identity matrix just does nothing. So what I mean over here is that when we apply the same gate twice, it does nothing. So it's very similar to what we just saw with the bit flip. X becomes, when we apply the poly X gate, the bit flip, 0 becomes 1, 1 becomes 0. So when you're applying it twice, so that's what we're indicating here. So when we add ket bras together, it doesn't affect the functionality of the original ket bras. Yes, that's exactly. So if we have over here, as we see, the presence of this one will not affect this. So unless you have something that's negating it or so, it won't affect it. Okay, so since we just saw what a bit flip does, what does the X gate do on 0? What does 0 turn into? Okay, 0 becomes 1. All right. And 1 becomes 0. I'm not even going to ask because, yeah, we all pretty much know that. And that is exactly what happens. So 0 turns into 1 and 1 turns into 0. Pretty simple. Now, what happens if we apply this gate to something that's not 0 nor 1? What when we apply it to the minus state? The minus state is a superposition of 0 and 1. It is in between 0 and 1. We can still apply this on any state that is quantum. So we launch a poll. It's okay if you get it wrong because this is the first time you're seeing it, but try it out. Take some time. Don't click on the answer right away. Try working it out on paper and see what happens. Note that this is a negative sign. So we have 1 over root 2, 0, minus 1 over root 2, 1. So what I want you to note is what does 0 change into, what does 1 change into, and what is our final answer. Note that our negative sign will not go away. Our negative sign does not go away. So when you're looking at, make sure to consider that. So it is on the survey. If you're unable to access the poll, you can message me the answer. Okay, I'm seeing some good responses. So I will leave that open for about a minute and quickly address someone else's question. How does alpha equal to u psi equal to, okay, so this is just the bracket notation again. If alpha equal to u psi, then so this is how you kind of write it out. So that's about it. If you transpose it accordingly, that is how it works. So this is addressing a question in the chat. All right. So once again, I want to highlight when you're looking at this, right? 0 changes and 1 changes. But note that there is a negative sign. That doesn't go away. So I think that might be the main place where people are wrong. So I see that most of you have answered. So it's totally all right if you're in the wrong, but we can try to learn this together, essentially. Okay, I will end the poll now. And share results. So about 28% of you have got it right. So let's actually see how this works. So we have x on minus, right? Which is equal to the x gate acting on 1 over root 2, 0 minus 1 over root 2, 1. So what does, now let's again multiply it out. 1 over root 2 x of 0 minus 1 over root 2 x of 1. So I'm just going to continue here. 1 over root 2. What is the x of 0? When we apply the x gate on 0, what happens? It's 1. Now what happens when we apply x on 1? Oh, this is a minus. It becomes 0. So now it's 1 over root 2, 1 minus 1 over root 2, 0. So we still have that negative sign. This is not minus either. This is 1 over the negative of 1 over root 2 of 0 minus 1. So this is minus of the minus state. And that is how we got minus of minus. So our answer is going to be option C. So when on each of this, when we have x outside, it acts on 0 and it acts on 1 to give 1 over root 2 of 1 minus 0 instead. And this is the negative state. I hope that is clear. And I will move ahead since there are no questions on the chat. Or maybe let me go one more question. Let's say we act on the plus state. So if we act on the plus state, is it going to give us, what is it going to give us? Feel free to put it on the chat. All right. Yes, I see correct answers. So once again, this is 1 over root 2 of 0 plus 1 in this case, because we have the plus state. 0 turns into 1, 1 turns into 0. So 1 over root 2 of 0 becomes 1 plus 0. And that is once again, just plus state. And that's where we are. So now coming to an important gate, which is the Hadamard gate. Till now, we just learned how to make 0 to 1, 1 to 0, which is pretty boring because that's just a regular classical gate. Even in the quantum realm, it's just a regular gate. It from 0 to 1, 1 to 0, doesn't do much on the plus or minus states. But now we learn how to convert a state from 0 to a superposition state and back. So now we see the Hadamard gate where the plus state becomes 0 and the minus state becomes 1, and vice versa. If we have 0 state and if we apply the Hadamard, it goes into plus, which remember is a superposition. If we apply it on 1, it becomes minus, which is again another superposition, which is again equal 0 and 1. So this is one of our most important quantum gates. So now let's see how it works. So multiply it out, but if you decide to, this is what you should get: 1 over root 2 of 1, 1, 1, and minus 1. This changes axis from x to z. Yeah, exactly. So it takes a qubit and puts it into an equal superposition of 0 and 1. Yes. It also does the opposite. If you have an equal superposition of 0 and 1, specifically plus and minus, it puts it to 0 and 1. So it does vice versa. So if you apply it twice, it the same state similarly. So you're absolutely right. It takes a qubit, and if it takes the 0 qubit and 1 qubit, not a random one. If you have either 0 or 1, it'll take it and put it into an equal superposition of 0. So now I'm going to launch one more poll. So notice how it takes 0 to plus state back to 0. It takes 1 to minus and minus back to 1. So let me launch a poll. What happens if I put if I put two Hadamards on our state psi? Again, I don't know why it says minus. Anytime I put it in the question, our psi turns into minuses. If I apply H twice, so if I apply Hadamard and Hadamard, remember that it takes it from 0 to plus. If I apply it again, it takes plus back to 0. So what happens when I apply it twice? All right, I'll give it a couple more seconds. Okay, I'm gonna end it now. Okay, so majority of you have got the right answer. So when we apply the Hadamard twice, it's going to give you the same thing back. So for example, so again, if we have 0, if we apply Hadamard once, so if we apply H to 0, it becomes the plus state. If we apply Hadamard again, it becomes Hadamard of H plus, H0, which is Hadamard on the plus state, to 0. So we get back the same thing. And the exact same thing happens if we have a random state as well. So let's remember psi from yesterday, alpha 0 plus beta. So now let's apply Hadamard twice on psi. So now that's equal to the Hadamard. So we've applied H once, right? So what does 0 become? If we apply H on 0, what does it become? Yes, so it becomes plus. So what happens when I apply it on 1 now? Hadamard on 1 becomes minus. So if we apply Hadamard once, we get this state. But now we have to apply Hadamard again. So what happens now? Alpha, what does plus become? 0. Beta times, what does minus become now? 1. So did we get back the same state? We got psi back. And recall that we can represent any state like this. We can represent any state as the linear combination of 0 and 1. So when we apply Hadamard twice to any possible quantum state, it is going to give back our original state. So now this is just a quick, I don't think I have any polls remaining. Yes. So this is just a quick mind map of what happens. Okay, someone's asking if we can get recorded sessions by any chance. These are all recorded. The previous link has been sent to your email. So just putting that out. In case you haven't, please check for an email from shraddhaangiras0911.com. If not, send me a message. I can send them over. Okay, so for the sake of time, I will, or rather confusion, I will probably not go over this right now. Give me 1 second. Let me see how much we have left. All right, so I will come back to this at the end of the session in case we do have time. You can stay for an extra 10 to 15 minutes at the end, and I will cover it. So now coming to multipartite states. So we've been looking at 1 qubit all along. We've been seeing how we can change a single qubit. But what have more than 1 qubit? How do we represent more than 1 qubit when we have our matrix form or vector form and so forth? So for that, we have something called the tensor product. So if we have n qubits, or dimensions, or the vector space is 2 to the power of n. So till now we had 1 qubit. So we had 1 entry, we had alpha and beta. But now if we have, say, 2 qubits, our dimension is, here it's 2 to the power of 1. Here, if we have 2 qubits, we have the dimension 2 to the power of 2 equal to 4. So we're going to have a vector that's, say, A, B, C, and D. We have, again, 3 qubits. It's going to be 8. So we'll have A, B, C, D all the way to, say, A8, A1, A2, all the way to A8. So it has 8 as a... So how can we represent this? For example, we have 2 qubits, both are in 0 state. So now let's see how we can represent them in this format. We use something called tensor products to describe qubit systems. So for example, we have our 2 states as usual, alpha and beta. So we have alpha is equal to A1, A2, and beta is equal to B1, B2. So now let's do the tensor product. We want to represent alpha and beta as a single vector so that we can do our, suppose, transformations on it if we want them to interact. So we can, so this is the symbol. We've been using the regular dot symbol for other multiplication. For tensor product, we use that. We use this symbol over here. So A1, A2 tensored with B1, B2. So this is just a notational thing. How we do it is we take A1 times the vector B1, B2, A2. So A1 times this whole vector, and A2 times this whole vector, B1, B2. So we just multiply it out. A1, B1, A1, B2, A2, B1, 2, B2. So we just multiply them out. We can see an example very soon. So you just take A1, B1, A1, B2, A2, B1, A2, B2 as our 4 entries. So let's see an example now. So let our system A or qubit A be in state 1 and system B or qubit, the second qubit, just be 0. So we just want to represent 2 qubits, one having state 1 and the next one having state 0. So instead of representing it like this, we can say 0, 1 tensored with 1, 0. Now let's see how that works. So 0 times, so we have 0 times 1, 0, 1 times 1, 0. So if you have a book and pen, follow along with this. So we have 0 times 1 is 0, 0 times 0 is 0. So that's this and this. Now we have 1 times 1 is 1. 1 times 0 is 0. So we have, this is our 4-dimensional state, our bipartite state, which is essentially just a representation of 2 qubits. So bipartite means if we have 2 qubits, this is how we represent it as. So if we have 1, 0, this is the vector notation for 1, 0. Because otherwise we have 2 vectors and we kind of don't know what to do with them. This is the appropriate way to represent 2 vectors in the 2 vectors there, essentially. So are we on the same page, or do you want me to do another example? All right, we're looking at another one. So instead of this, consider give me 2 states, 2 random states. Probably give me zeros and ones. Do you want 1, 0, 1, 0, 1, 1, 0, 1, 0, 0? Which one of, oh, sorry, I think I sent that to someone particularly. Okay, so let's do 0, 0 maybe. Okay, so I'll go back to this slide because this probably, so you can see the exact multiplication together. Okay, so now let's do 0, 1. I got quite a few 0, 1s for whatever reason. See if there are any questions before that. So now let's take 0, 1. So 0, 1 is just 0 tensored with 1. Okay. With complex numbers, can you do? Yes. And we can also take plus and minus. If you want, I can do that as the next example. We can do a final example to finish things off. So 0 is 1, 0, right? And 1 is 0, 1. Let's multiply this out. we have 1 times this vector 0, 1, and 0 times again this vector 0, 1. So now what's going to be the first entry of my vector? What's going to be the first value I write now? Yes, it's 1 times 0, which is 0. Next one that I will write. 1. Yes. So it's going to be 1 times 1, which is 1. So the next two are pretty obvious. It's going to be 0 times 1. So 0, 0. So this is how we represent two qubits, the first being in 0 state and the second being in 1 state. So this is how we know it is 0, 1. We can kind of as well because we know A1, B1 is equal to 0. So if you want to do the opposite, because someone asked me, if you have this, how do you know it's 0, 1, right? So we can essentially compare this. A1, B1 is equal to 0. A1, B2 is equal to 1. A2, B1 is equal to 0. A2, B2 is equal to 0. So it's pretty obvious that A1 is A1 and B2 are both 1. So we have A1 as 1 and B2 as 1. And the rest, because of normalization, because the length is 1, right? If B1 is anything other than 0, it's not going to work out because the length of our vector will be more than 1. So this is 0 and this is 0. So we can get back our original states by just comparing this with this. Does that make sense? We can quickly do, oops. We can also quickly go over how plus and minus goes about. I have clear pen markings. Okay, so we're a little bit on a time crunch, but I will try to go ahead as quick as I can. So if we have plus and minus, we can still do it. So this is 1 over root 2 of 1, 1, tensored with 1 over root 2, 1 minus 1. You can either multiply this inside and work it out as well, but for the sake of simplicity, we can multiply out the constants. So 1 over root 2 times 1 over times 1, 1 tensored with 1 minus 1, which is equal to half. So what is 1, 1? 1 times 1 is 1. 1 is minus 1. 1 times 1 is again 1. 1 times minus 1 is minus 1. So this is what happens if we tensor plus and minus. So plus tensored with minus gives us this funky state. But it is a valid state. It is entirely valid. So now moving ahead. So we just saw how this works. So this is our fourth postulate of quantum mechanics. Separate quantum system by the tensor product of the separate individual Hilbert spaces. So this is a simplistic way of saying our quantum system, which is say a 2-qubit system, is the tensor product of the individual spaces. So it's the tensor product of our individual qubit 1, individual qubit 2. When we take the tensor, we can describe our overall product. And so, yes, that's just stating it better. So now we just saw the tensored version of things. Why do we need that? So unless I'm going to actually manipulate these two qubits, there is no point of using these gates, right? So not only do we have single qubit gates, we have multi-qubit gates. The 2-qubit gate, the CNOT gate, being the most important of them all. So this is a gate that acts on 2 qubits at once. So let us see how this works. So say we have 2 qubits. So first off, just explain the structure of it. So this is our gate over here. This top region is called the control. And then this is awfully similar. Where have we seen this symbol before? If anyone can remember, I mentioned it in passing. Yes, that's the poly-X gate. However, it's connected. So this is currently called the target gate. And notice that it will perform the X gate in some capacity. So what this does is this gate essentially remains. When it is applied, this gate asks the control qubit, are you 0 or 1? If it is 0, it does nothing. So here you can notice, so this is 0. The gate asks, is control 0 or 1? The control qubit is 0. So it does nothing. So if 0, 0 qubits that go in, nothing happens. So the control is unchanged and the target qubit is unchanged. However, when we send in 1, this is the control, again, and this is the target. So when the controlled qubit is 1, the target qubit flipped. So the control qubit remains. So we've sent in 1, 0. So the gate asks, is the control qubit 1? Yes, it is 1. So the target qubit undergoes the X gate. So on 0. So 1, 0, it checks the control. Control is 1. So it becomes 1, 1 because the target is flipped. So now let me ask you a question. So say we have this. Again, this is our CNOT gate. We send in 1 and we send in 1. So what are the 2 qubits that come out now? Notice the control qubit is 1. The target qubit is 1. So one of this undergoes something. Yes. We're all on the same page, correct. So the control is checked. The control is checked. The control is 1. So now the target is flipped. Target is flipped. So does it change? Is the control changed in any way? Does the control remain the same or does it change? It's the same, yes. So the control remains the same. Now the target undergoes the flip. So 1 becomes 0. So we notice that 1, 1 becomes 1. All right. So now what do you think happens in this final scenario? Oops. we have 0. What happens here? Okay, we're all seemingly on the same page. It remains the same. So it checks the control. The control is 0, so it does nothing. So both of the qubits remain unchanged, 0 and 1. So only undergoes a change every time. The control qubit always remains the same. The 0 always remains the 0. 1 remains 1. Control gate which can change the qubit of another X gate. Sorry, I don't think I got your question exactly, but I'm assuming you're trying to clarify this. So this is just, so we can have a control qubit, a target. This target doesn't always have to be an X gate, but that's what we traditionally use. We can also have like a controlled Z gate where instead of flipping over the X axis, it can do the Z axis as well. Can you won't change. So it's essentially the only thing the gate does is asks control which state it's in. If control is 0 or control is 1, if control is 1, flips the target. So it flips the target qubit. It doesn't do anything to the control. Else does nothing. So essentially the asks, are you 0 or are you 1? If it is 1, the gate, because it's a connected 2-qubit gate, acts on the target qubit instead and flips it. And so that is how so now let's come to the Dirac notation. Is the purpose only to entangle states? One of the purposes is to entangle states. We can do a lot more as well. So 2-qubit gates is the fundamental way to interact. So entanglement is not the only way that things interact. For example, we can have simulations of molecules. In that case, we want our molecules to interact in a certain way, and that's where 2-qubit gates come in. So if we want to change a qubit based on something else, we definitely need this. So it's pretty fundamental in quantum computing. So one more great question is, instead of 1 or 0, what if we pass plus or minus? We will get to that. So that is where entanglement comes in. So we will see that very soon. Good question. So now let's just look at the Dirac notation. We just saw how it works. And let's mathematical form, right? So 0, 0. So we represent the gate as seed X. So what happens when we apply 0, the C naught 0, 0? This is control. The first one is always control, unless otherwise specified. Target. What happens? It's, yeah, I'm seeing right answers. So we get 0 and 0. Okay, so what happens for 0 and 1? What about 0 and 1? Does anything change? It doesn't. It's again 0, 1 because the control is still 0. So it's 0, 1. Now, what about 1, 0? 1 is the control. 1 becomes 1, 1. Now, what about 1, 1? It becomes 1, 0 because the target qubit is flipped. So now that we have the sort of idea on how it acts on these qubits, let's now construct our unitary in Dirac notation. So 0, 0 becomes 0, 0. So 0, 0. Let me write it somewhere where I can fit everything. So that's what we see over here. I've already written it in text, but we're going to go over it again. 0, 0 becomes 0, 0. And that's our case 1. So what does 0, 1 become? 0, 1 turns into 0, 1. It remains the same thing. So we finish our second case. Now our third case, right? We have 1, 1. What does 1, 1 turn into? 1, 0. Our third case is thus done. And our final case, 1, 0, turns into 1, 1. And that is how we represent our C0 gate in Dirac notation. And if you multiply it out, it looks just like this. And that's the example that we see here as well. When we apply C0 on 1, 0, it becomes 1, 1. You can multiply it out, use the tensor format, everything to see that this truly does work. So now finally we get into entanglement. So I hopefully can finish this within time. Go through it as slowly as I possibly can. So once again, to go over the concept of entanglement, in case you missed it or you might have forgotten a bit, it's called spooky action at a distance, but we can essentially do this weird magic between two qubits and then put them into, they are now entangled. You can put them into boxes, ship or separate them essentially by any distance. So for example, I have two entangled qubits. I've shipped them halfway across the world. If I decide to measure this qubit, if I decide to take it and measure it, if it's a photon, I can pass it through a filter, I can observe it, ask my qubit, are you 0 or 1? Instantaneously, for whatever reason, in the quantum realm, our other qubit also turns into the same thing. So if my wave function with my qubit over here collapses, instantaneously, the one that may be light years away or half the world away, also for whatever reason, instantaneously collapses in the quantum realm. So if I get a 0, so will the other person. So now, and in entanglement, we have 4 main Bell states. So these Bell states are what we call maximally entangled states. So what we just saw over here previously, over here, the 0, 0. Whenever I have 0, the other person has 0. Whenever I get 1, the other person will also get instantaneously 1. That is one of our Bell states. So that's what in Dirac notation. So everything can be reduced to a bunch of math. So 0, 0, when I have, so we can represent this as two systems, right? If my qubit is 0, the other person's qubit is also 0. My qubit is 1, your qubit is also 1. So that is one of our Bell states. So again, here as well, if I have 0, you will also instantaneously have a 0. If I have a 1, you will also There are also other two Bell states where the opposite happens. If I get a 0, you will 100% of the time get a 1. If I get a 1, you will get the opposite. So we're not going to cover this right now because it probably confuses things. But we're now going to try and create this state. So it sounds pretty fascinating to create an entangled state, but we can do this with just two gates. If we have two qubits and two gates, that's enough to entangle two qubits. And let's see how we can do that. So there's a question, why do they both collapse to the same state? That's how it works in quantum mechanics. So that is why Einstein thought it was really weird, because he felt like one thing affecting something light years away in the universe didn't make sense. But we have experimentally proved that this occurs. So now our goal is to take our base states 0 and 0 and finally convert them to be the end state. So this is equal to 1 over root 2, 0, 0 plus 1, 1. So that is our end goal. So let's go about doing that. So first step in the process is applying a Hadamard gate. So Hadamard gate needs to be applied only to our first qubit. So now we initially started out with 0, 0. Applied the Hadamard gate. So we now have plus and 0, plus tensored with 0. Oops, sorry. Give me 1 second. Okay. How did 1 over root 2 come? Oh, that's a good question. One thing that you need to note is, again, all of our quantum states have the length of 1. So we need this. So writing this out as a vector, it's going to be root 2, 0, 0, 1 over root 2. So when we take the length of this, it's going to be the square of 1 over root 2 plus square of 0 plus square of 0 plus square of 1 over root 2, which is half plus half is 1. So all our quantum states must be unit vectors in the Hilbert space, as we saw in our first postulate. So it must always be a unit we see over here. So one thing to note that brings about a good point that I wanted to cover. So suppose we have, I'll cover this on a different slide so that we don't get confused. Or rather, I'll just cover it here maybe. So note, yeah, okay, it's loading. Note, say we have A, C, and D, right? So A square is the possibility of getting 0, 0. B square is the possibility of getting 1. C square is the possibility of getting 1, 0. And D square is the possibility of getting 1, 1. Right? So now in this scenario, we know that there's a 50-50% chance of getting 0 or 0, 0 or getting 1, 1. So there's a 50% chance that both of us get 0, 50% chance both of us get 1. There's no chance that we get the opposite signs. So what happens? So 50% chance, this is the probabilities. Over here. So half of the time, we get 0, 0. So A is going to be the root of half, 1 over root 2. What's the possibility of us getting signs? What if I get, what is the possibility of me getting 0 and you getting 1? Put it on the chat. Is there any possibility? I'm seeing correct answers. No, yes. So we won't be getting opposite signs at all. So in an entangled state, when I get 0, you get 0. When I get 1, you get 1. There's no chance of anything else happening. So this is going to be 0. If I get 1, the possibility of you getting 0 is nothing. So 0. So if I get 1, what's the chance that you get 1? Yes. 1 over root 2, 0, 0, 1 over root 2. And that is our representation of our current Bell state. So this is the state that we want it to eventually reach. So again, coming to another example, a quick secondary example. For example, we have, say, the state 0, 0. Then the possibility of getting 0, 0 is, so 0, 0 is just represented as A is equal to 1, B equal to 0, C equal to 0, D equal to 0. So the chance of if you want to write 0, 1, then the chance of getting 0, 1 is 100%. So 100%, B is 1. So 0, 1, 0, 0. ABCD represent the probabilities of an entangled state only. Not exactly. It just represents the positive having the state 0 and 0, the state 0 and 1, the state 1 and 0, the state 1 and 1. So if we both have zeros, it's not entangled, just a regular state. If we just have 0, I have 0, you have 0, then we come, this is our state. So I hope that's clear, and we will go ahead. So now first, we apply the Hadamard gate on our first qubit. So coming back to this, we initially always have an empty sort of circuit. Where's the clear pen markings? Yeah. So we have first we have just this, right? So ignore this portion of the screen. Just have a circuit where both my qubit and your qubit are in 0 state. So now the first step is to take my state, or one of our states. Let's consider this to be me, this to be you. So let's take my qubit and put a Hadamard gate on it. Right? So we can view this in Dirac notation as well. Now that my qubit has a Hadamard on it, what is my qubit? I applied Hadamard on 0. So what's the value of my qubit? Yes. So my qubit is now the plus state. So I have plus, and you still have 0. So I have plus, you have 0. So let's see that in tensor form, right? So I have plus me, and you have 0, you. So that is 1 over root 2 of 1 minus 1 and 1, sorry, tensored with 2, which is 1 and 0. This is equal to 1 over root 2, 1, 0, 1, 0. 1 over root 2, 0, 1 over root 2, 0. Okay. So that is the state that we are in. So we can also represent this in Dirac notation in a different way. So I plus state. So 1 over root 2, 0 plus 1 over root 2, 1 is me. And you have 0, right? So now what? If we tensor it together, in Dirac notation, it's pretty simple. This is why we use Dirac. Instead of having to tensor it out, 0 tensored with 0 is just 0, 0. And 1 over root 2. 1 tensored with 0 is just 1. And that's how we simply write it out. So this is our state. So now our combined state looks like this. And that's what we see here. Our combined state, you and I have the state together in Dirac notation. So now what we do is we just apply the Hadamard. We apply the C0 gate, where I am the control qubit and you have the target. So we just apply this. So now so till here, right? Till this point, we have the combined state of, so this is not in superposition yet, because I have the plus state, you have 0 state. We are not combined in any way. I'm just writing this together to indicate the final state. Which is equal to just plus and your 0. Now, since we have our C0 gate, things change. So now if you remember, now we were just applying C0 on our combined 1 over root 2, 0, 0, plus 1 over root 2, 1, 0, which is equal to 1 over root 2. I'm just going to take the constant out. Hope that's not too confusing. C0 on 0, 0. C0 on 1, 0. So we have our constant once again. What is the C0 applied on 0, 0? I am the control. The first qubit 0 and your target 0, 0. Now I'm the control. I have 1. It's 1, 0. What is C0 applied on 1, 0? It is 1, 1. Exactly. So now we have a state that is entangled. Now, after applying our C0, we have our final Bell state that we've been looking for. By applying just 2 gates, we have now our qubits. So even if we are at an infinite distance apart, if I am light years away from you, our qubits are still entangled. And so if I measure the qubit that I have and I get 0, then yours will instantaneously also turn 0. When I measure mine as 1, yours will also instantaneously become 1. The thing about the measurement is it's random. So I cannot choose whether it becomes 0 or 1. But the thing is, yours will also instantaneously become the same thing. So if I get 0, yours will get 0. If mine decides to become 1, yours also decides to become 1 at the same. And that is how we construct one of our Bell states. The rest of them can be constructed in very similar methods, just with slightly different gates initially before applying the C0 gate. That is why our C0 primarily called it's generally called the entangling gate, if I'm not wrong, because it is used for entanglement. So one of the questions, do we have to measure both qubits at both ends simultaneously? No, we don't have to measure it, because if I measure mine, yours is in a superposition, yours is in a random state. It's in between 0 and 1. But as soon as I measure mine, yours immediately turns into whatever mine is. You don't have to measure it. You can measure it here, measure it at the same time. Anytime you measure it, it doesn't matter, because as soon as mine collapses to one state, yours also collapses to the same thing. So as soon as I look at mine and it decides to turn into yours also, even though no one's looking at it, it decides to turn into 1. What happens if we measure both together? Measuring both together, again, in terms of theoretically, it should again be the same thing. So if we measure the same thing, will decide to be the same state. Theoretically, that is what happens. Practically, we will be unable to measure them exactly together because of physical constraints, but that is what happens in theory. In theory as well, even if we measure it at the same time, yeah. When we measure 0, will it remain 0 as long as we're observing it? Yes. So even if we stop observing it, it'll still be 0 because it's collapsed. So again, coming back to the light example, if we pass it through a filter, once it passes through the filter, it's now horizontal. It's not going to go in between horizontal and vertical. It's already passed through. It has chosen to be horizontal. It's chosen to be 0. And forever, it's going to be 0. So essentially, what I'm trying to say is if both of our qubits are entangled and I pass my qubit through a filter, through, say, a Polaroid filter, if mine goes through the filter and becomes 0, then your 0. So whenever you decide to take your qubit and pass it through a filter, it will 100% pass through. However, if the opposite happens to me, yours will never enter the filter. Because if mine turns into 1 and it doesn't enter the filter, yours will also never enter the filter. Will this hold true for more than 2 qubits? So for more than 2 qubits, we actually have something called GHZ states, if I'm not wrong. GHZ or yes, GHZ states, I believe. And those are 3 entangled qubits. So you can have multiple entangled qubits, but we generally don't use them. Can we bring back a collapsed qubit to its original state? We can, again, if we have entangled qubits, both of us need to come together once again to re-entangle them. If we are light years apart, we can't put them back to their original states. But if you have something like a plus state and you measure it and it becomes 0, again, we can put it back to its original state. So as soon as we measure one of them, the other just changes without us measuring it. Yes, it changes without us measuring it. So we don't have to measure the other qubit. If I measure mine, you don't even have to measure yours. Yours is already collapsed. So yours has already gone from its entangled state to 0. So if you measure it, if you don't measure it, it doesn't matter. Yours is now, it has its fate decided as 0, essentially. So one thing to note is that entangled states are not separable, which means you can't untensor them. Because now our qubits are essentially entangled. But now, if we go back to our comparison, right, of A1B1, A1B2, A2B1, A2B2, this is a tensor product, right, of A1 and A2B. If we compare this to any of our Bell states, you will never get a solution for A1, A2, B1, and B2 that is valid. So whatever you try, this cannot be solved. So you can't untensor them. So entangled states are thus untensorable. If we can't control a qubit, how a qubit collapses? So we can control how a qubit collapses in terms of, say, we can choose the basis in which it collapses in. When we consider something such as a regular like plus state collapsing to 0 and 1, it's practically useless because it's just a random, it essentially helps in generating random numbers. But you can use the properties of quantum computing to have something to eventually get to a state that's, say, 99% 0 and 1% 1. After doing computation, it is state. So once you collapse that qubit and you redo the experiment, say 100 times, you know that 99 times it collapses to 0. So 0 is probably your answer. So the key lies in the computation. So taking a generic plus state isn't going to do anything because it's just going to give you a random either 0 or a 1. If you take a superposition of, say, like n states, you'll get 1 of 2 to the power of n numbers. But that's useless. What's the point of just getting 1 of 2 to the power of n numbers? However, when we're doing computation, when we're doing something, say the Grover search algorithm, where you have an unsorted database, each of our entries have one associated number with them. And once we perform our search algorithm, we will see that we'll see, say, a graph. It has 0, 0, 0, 1, 1, 0, 1, 1. And you can scale this up to n qubits. So when you perform algorithm, you'll see a peak in one. So for example, we've done the experiment 100 times. So there's a peak in one of them. The rest are like this. So we know that 1, 0 is is what we're searching for. So what is in the third entry? So how is this possible? What is causing it to change? What is causing the information to pass on between the qubits? So one thing to primarily note, so one theory in physics is that you cannot have the transfer of information that is faster than the speed of light. So no information can be transferred quicker than the speed of light. However, I was just mentioning that entanglement is instantaneous. The thing with entanglement is that no information is passed because it's random, right? We have an entanglement where there's a 50% chance 0, 50% chance both of us get 1. I cannot definitively say I want to pass the information of 1 to you. I cannot say I want to collapse my qubit into a 1. It happens on its own. It is random. So thus, information cannot be truly passed quicker than light. But the reason this collapse occurs is, again, weird quantum mechanics. Quantum mechanics is just unintuitive. Why this happens is something that we cannot really explain. It works, that it collapses, but we don't know why it works, essentially. All right. So once again, thank you all so much for coming. We will be sending I have sent an email that contains the recording of yesterday and a sort of poll asking what time would be the best for the trivia. So please fill out that form. I will again with today's recording so that I know which time is the most comfortable for you to attend. So this will be online, and in case you have some extenuating circumstances where you cannot attend, we will accommodate for that as well. Just send me an email. So coding notebooks, these are completely optional. They'll be sent today for me, which is probably tomorrow for you guys in time zone. So it will eventually reach your inbox, hopefully not at a really weird 1 a.m. time. And certificates will be sent this week. The trivia and the coding notebooks are optional. You can you don't have to do them to get the certificate as long as you've attended 60% of the total duration of yesterday. So all you have to do is fill the feedback form and do a 5-minute quiz so that I know to what degree learning has occurred from these 2 sessions, so that I can, again, modify my upcoming sessions as well. So again, this will also be sent with the coding. It will be today/tomorrow for you guys. So thank you all once again. If you have no questions, this is it. I hope to see you again next year or any other time if you would like to attend any of our courses. So you can head over to quetzal.co.in. So if you want to either work with us or if you want to learn from our courses, feel free to visit the website and sign up. And thank you all so much for coming. I will stay for a bit in case there are any questions. And that's it from me. Thank you all so much once again. It was great hosting all of you. Okay, I will cover the poly-Z gate. So that's again optional, but if you'd like, we can cover that as well. So I will quickly go over to those slides. Meanwhile, feel free to ask any questions related to yesterday or today on the chat, and I will answer them as well. There's the Z gate right over here. So we learned how to the spin of a particle. Okay, so I'll just address that quickly. The spin of a particle is something that you will probably learn in grade 12. That's more of a physics concept. It's occasionally used in quantum computing. I wouldn't say if I said the exact definition, I would do justice to it, but I can cover it right after this, if that's okay. I'll just write it down to cover. Okay. All right. So send any questions you have on chat and I will answer them right after this. So we learned how to convert from 0 to 1. So how we can go from the 0 state to the 1 state back to 0. That was the X gate. We learned how to put things into superposition. So 0 to plus, plus back to 0. 1 to minus, minus back to 1. But what we haven't seen is how to convert between plus state and minus state. So one thing that you can do, for example, if we have the plus state, want to convert it to the minus state, what we can do is apply the Hadamard gate. The Hadamard gate will give us 0, right? Then we can apply the X. Wait, let me go through this with you all. Okay, so what happens if I apply the Hadamard on the plus state? If I apply H on plus, it's gonna give me 0, minus, 1. Does anyone have an idea? Okay, yes, we got a 0 in the chat. Yes. So this is going to give us 0. What we can do is we can convert this again to 1 by applying the x gate. So x of h plus is going to be the x of 0, which is equal to 1. So can I convert 1 to minus with something that we already know? When we apply something to 1, it turns into minus, the Hadamard gate. So we can do, let me go back to that. Sorry. So if we apply Hadamard again, we get the Hadamard of x0, which is the Hadamard of 1, which is now equal to the minus state. So we can convert the plus state to the minus state by applying h, x, h, gates in continuum. However, there is an easier way, sort of, to do that. Sorry, I went to the wrong slide. So there is another way to do that, and that is called the poly Z, or the phase flip. So here we are flipping from the plus state to the minus state, and minus state back to the plus state. So if you have gone through the slides that I sent yesterday in the extra section, there was something called the block sphere. So we can represent all of these states on a sphere, and so that's why it's called poly Z. But if you didn't go through it, that's totally okay. This is just complicated. So it turns minus to plus and plus to minus. And that is very similar to indicating turning 0 back to 0 and 1 to minus 1. In fact, we can see that, right? Say we have plus is equal to 1 over root 2, 0 plus 1. So ignore this portion. Ignore this for now. We know 0 is converted to 0 and 1 is converted to minus 1. So what happens if I apply the Z gate on plus? 1 over root 2, what does 0 turn into? If we apply Z on 0, what does it turn into? It becomes, yeah, I see some right answers on chat. 0, because 0 turns into 0. And what happens to 1? Does it become 1 or does it become negative of 1? Becomes negative of 1. Now what happens is this is the minus state. So that same process occurs if we apply Z on the minus state, it becomes plus. So when we apply Z to 0, we get 0, as we see over here. Apply Z to 1, it becomes minus 1. Plus becomes minus, and minus becomes plus. And that is how we write it out. So that is pretty much it about poly Z gates. This is one of the other axes in which we can flip. There's also the poly Y gate, which again, we can construct using other gates. One thing is, in many quantum computers, we do not end up although we can code on our computers poly Z gate, poly this and that. On our actual quantum computers, there are only a certain specified set of gates that they have. So they'll have the C0 gate, they'll have the poly X, the Hadamard gate, and so forth. So instead of actually having a Z gate that they will apply, instead, as we just saw previously, the Z gate does the same action as applying x h x. So even though on our computer z, we can say, hey, apply the z gate on qubit 1. The quantum computer will instead do x h x. So that is something that's just an interesting fact. Oh yeah, it's h x h. Sorry about that. You are indeed right. Yes. So it does x, does h x and h. So this is just some interesting things to note about quantum computers. So that also, even we can also have more than, when we come to like 3 qubit gates, 4 qubit gates, they can have something like 3 control qubits and 1 target qubit. And things like that can be constructed from our preliminary gates, such as using multiple C0s and so forth. Probability measurements of Y basis. Okay, I will send the answers over because that will take a bit of time to actually put right now. Let's see if I have them already. If not, I will send them over. Let's see, or we can actually do that if there are no other questions, honestly. Yesterday's class before Dirac notation. Yesterday's class before Dirac notation was just about how quantum computers work. So if you go through the slides or the video, that should be enough. It was just a basic introduction about quantum computing. No actual information was covered. And all right, finally, if we need to do the Y basis measurement, we can go ahead and finish that up. I'll just add another slide maybe at the end. Okay, so let's write out our Y basis. Plus I is equal to 1 over root 2, 0 plus I 1 minus I is equal to 1 over root 2, 0 minus I1. And now let's take our psi equal to alpha 0 plus beta 1 as usual. Okay, so now let's go ahead and find the probability of getting. One second, let me check the chat if there's anything else. Why do we use the complex plane? That is pretty much how we define our Hilbert space. So when we look at quantum mechanics as a whole, imaginary numbers help us realize a lot of things. So that's the best explanation I can give in basic terms. If that's okay, sorry. But I will finish up with the Born value that people are asking for, plus. So the probability of getting plus I is going to be equal to plus I with, give me 1 second, something else on chat. Okay. psi whole square, right? So now we have 1 over root 2, 0. Okay. Yeah, 1 over root 2, 0. And now we've taken the ket version, right? The bra version of our ket. So we x conjugate, which is minus I. And now we have psi, which is alpha 0 plus beta 1 whole square is equal to, if you multiply this out, there's a smaller bracket in here, 1 over root 2 of alpha 0, 0 is this one, plus beta of 0, 1 minus I times alpha. This is okay, sorry, I've messed up a little bit of the notation. Alpha 1, 0 minus I beta 1, 1. So we can cancel out 1, 0, right? So this goes and this goes because the dot product anyway. So 1 over root 2 alpha minus I times beta whole square. So that is the probability of getting plus I. Oops. Zoom in. Equal to half of alpha plus I beta whole squared. So doing this for minus I is also going to be very... So I'm just going to do it a little bit shorter up there. So the probability of getting minus I is going to be equal to 1 over root 2 times 0, since we're taking complex conjugate, plus I1 alpha 0 plus beta 1 whole square, which is equal to 1 over root 2 alpha 0, 0. I'm going to not write out the cancelable terms, if that's okay, plus I beta 1, 1. So that's equal to half of alpha plus square. And so you can confirm that this also, the two probabilities will add up to 1. Doesn't psi change in different axes? I'm not sure what you mean by that. Do you mean like the representation? Like, do you mean it should be represented as alpha plus I and beta minus I? So one thing to note is that any state presented as the linear combination of any basis. So we can write this. Let me keep those. So essentially, you can write psi like this, or the same psi is equal to half of alpha plus I beta, or rather 1 over root 2 of alpha plus I beta times plus I plus 1 over root 2 alpha minus here this is minus I beta minus I. So note that that 0 and 1 as well as plus I and minus I are all different bases. So you can represent any given state as a combination of linear combination of 0 and 1, or as a linear combination of plus I and minus I, or as a combination of plus and minus, or any two orthogonal states. You can represent any vector. So in this case, I chose 0 and 1 because that's a standard way of doing it. But this is the same as this weird form is the same as writing it in terms of this is psi. Sorry, my thing is, yeah. So I hope that's clear. So here we're using we're using 0 and 1 because that's the most that's convenient. Web page representation of psi is different in Y basis. Okay, yeah. So it depends on what you're looking for. So some people will represent the initial plus and minus spaces. So if I took, say, let me add another slide. So for example, if I took psi as alpha I and beta minus I, then the possibility of me getting plus I on measurement is alpha square. The probability of me getting minus 1 on measurement is beta square. So this actually, so if I'm measuring probability of getting plus I is alpha square, probability of minus I is beta square, because we are representing it as a linear combination of plus I and minus I. The reason I showed with 0 and 1 is because sometimes you have different bases and you want to measure it differently. So in this case, it's just our general trick. So if we are measuring in this basis, it's just alpha square. If you're measuring in minus, you want to see minus is beta square, beta magnitude square. Okay, so I'm reading a question on the I have a theory on why quantum entanglement happens. So basically consider two qubits having equal probabilities of 50-50. Quantum entanglement is basically matching their probabilities to get the same state instantaneously. The thing is, both of our qubits will be at a 50-50% chance of becoming 0 or 1. So they don't match probabilities, but rather they collapse entirely. So once I measure mine, yours instantaneously becomes the same state. So the theory on how the universe works, there's a lot of different theories that float around. There's just so many, and different people have different opinions on it. So none of our theories have substantial proof for them. So you can look them up. There's the many worlds theory. Then there's something related to quantum gravity. I'm not sure of I don't remember the exact name. There's also string theory. So yes, psi and minus psi in Bell states. Can we entangle qubits to have different probabilities? I believe so. While I haven't seen it particularly, that's That's a good question. I can get back to you if you email me with that because I'm not too sure, honestly. Good question. What is psi and minus psi in Bell states? And let's go over that quickly. So these are just different Bell states. So in this scenario, this is the opposite of what I've been describing. If we entangle our qubits to be psi plus, whenever I measure my qubit and I get a 0, you will get a 1. Whenever I measure 1, yours will collapse to 0 instantaneously. So instead of ours having the same sign, same number, it becomes the opposite, the exact opposite. So we both will never have the same state, is what it seems to imply. So that's what psi plus and minus are. If one has probability of 1 and the other towards 0, we cannot do that in particular. So essentially what happens is their probabilities need to add up to 1, right? So the probability of both of us getting 0 or both of us getting 1 need to add up to 100. So we can unfortunately not have that. So if 2 qubits are entangled, there's a 100% chance that when we measure one qubit, the other collapses to the same state. Yes. So it collapses either to the exact same state, or if we're taking psi plus and psi minus, the exact opposite state. Essentially, there's a correspondence. So in the first two states, it always 100% chance that it collapses to the same state. If we've taken these two, it 100% collapses to a different state. But yes, pretty much, you've got the exact correct idea. What's the last expression on this slide? Oh, this expression is the one that I was talking about. So if we have, so we can indicate tensor products. If we have, say, A1, A2 as alpha, tensored with B1, B2, it's equal to A1, A1, B2, A2, B1, A2, B2. And the thing about this is if we have our entangled state, if we write our entangled state out as, say, for example, let me choose psi plus, right? Psi plus is 1 over root 2, 0, 0, 1 over root 2. The problem is I cannot solve this equation. So if I have A1, B1 equal to 1 over root 2, A1, B2 equal to 0, A2, B1 equal to 0, and A2, B2 equal to 1 over root 2 is not solvable. So essentially what this means is once we have an entangled state, the entangled state is, you can't untensor it as two separate. Do anti-entangled qubits exist? Like if one collapses to one state, the other collapses state. Pretty much. I mean, if you consider 0 and 1 to be opposites, then yes. So that's what psi plus and psi minus are. So whenever I get 0, you get the opposite 1 state. Whenever I get 1, you get 0. So they're not anti-entangled, just in the opposite manner. And so someone was asking about spin. So essentially, if we're talking about spin as a whole, it's the angular momentum of our elementary particles like atoms, nuclei, and so on. So this is used in quantum computers, in certain quantum computers, if I'm not wrong. I'm not particularly good at I'm not particularly aware of the hardware part of quantum computing and how there are implications in that sense. But there are quantum computers that are based on the spin of particles. So unfortunately, that's the best I can explain it. I'm not I'm not very well versed in quantum theory as a whole. All right, so I will end this session. If you have any uh, questions, feel free to email me. Again, message me on Discord. I will reply with them. I think Discord, I personally say Discord because it's easier to attach images if you have any questions with regard to that. But if you have generic questions, feel free to email me. I will once again send over the code, trivia, and so forth. If you aren't getting emails, just email me and I'll send you the message back. But ideally, you should be getting an email from shraddhaangirus0911@gmail.com. So thank you all once again. Have a good night.